In today's lesson, what I want to show you are some of the experimental techniques that we use when evaluating chiral compounds. One of the oldest methods that we have for evaluating chiral compounds is in an instrument called a polarimeter. The polarimeter takes advantage of plane polarized light. So if you look here on the diagram, you see this is just a typical white light source, a standard light bulb. And when that light comes off, when the photons come off of a light source, they travel in waves. And the orientation of those waves can be any way. You can have some waves that are going up and down inside of the plane of this screen, traveling as a wave, some that are perpendicular to the plane of the screen, and every other angle imaginable. That's what's happening when light's coming off of just a normal white light bulb. And you can kind of think about it like snakes slithering like sea snakes slithering, and they can slither in any direction. And then what you do is you place a polarizing filter in their way. And the polarizing filter acts kind of like a white picket fence. So doesn't have to be white, just a picket fence. So the picket fence has openings that some of these snakes can slither through, but only if the snakes happen to be slithering in such a way that their wave, now we're moving back from snakes to photons, the wave of the photon has to line up with one of the slots in the picket fence. And so you can imagine polarizing filters that have very, very, very narrow slots between the fence, or some that are a little wider, and that's what you would pay for in terms of the quality of your polarizing filter. And polarizing sunglasses work based on this principle. They just kind of block out any photons of light that are not, that don't have a wave that is parallel to one of the openings in the picket fence. So the purpose so far of this polarimeter is to generate light and then to only allow light through this first polarizing filter that is polarized. So this is normal plane polarized light. And by plane, we don't mean P-L-A-I-N, where it's simple or easy. That would be plane. This is plane where all the light is in the same plane right now. Then you have some type of transparent tube. Think about like a glass test tube that contains your sample. And what we find is that chiral compounds will rotate plane polarized light. So as these photons are coming through this glass test tube full of a liquid solution containing your chiral compound, when those photons collide with the chiral center, they get twisted by a very, very, very small amount. But by the time the photon makes it all the way through your container, it will have smacked into many trillions of chiral centers. And so the result of all of those collisions causes the light that's exiting your sample tube to have some net rotation associated with it. And this is a useful technique because the amount that the light gets rotated is a function of the individual molecules as well as the number of collisions that occur. And we can control the number of collisions experimentally, and I'll explain that in a second. And once you factor that out, what you're left with is you can mathematically determine how much each molecule has caused the light to rotate. And that value, that individual rotation, or what's called the specific rotation, is unique to each molecule. It's kind of a fingerprint of the compound. So your plane polarized light enters your sample tube. It gets turned because of its interactions with your chiral center. And then you have a second polarizing filter, and you can think about just turning this like a kaleidoscope with your hand. And unless that second polarizing filter matches up exactly with the plane of polarized light, then all you're going to see here is darkness, because those photons are going to splash against this picket fence. And unless you've turned the picket fence so that it matches the resulting wave of light, then you'll see darkness. So you just adjust this polarizing filter until you get the maximum amount of light through the system, and you look at how the angle of the slots in your picket fence changes from your original polarizing filter to your final polarizing filter, And that difference right there is what's referred to as the angle of rotation. Now, in the modern laboratory, this whole process is automated. Your only job is to zero out the instrument. So what it does is it passes the light through a stationary polarizing filter. You don't have any sample here, or maybe you put your test tube in there with water, which is not chiral, so the light does not rotate, and then it records the second polarizing filter's angle as being the 0 point. Then you remove the blank, the test tube that contains only water, and you replace it with a test tube that contains some substance, and then you actually start to see the light get rotated. Out of curiosity, one semester I put Diet Mountain Dew, which is my favorite beverage, inside of this container, and the artificial sweetener associated with Diet Mountain Dew is a chiral compound. There's also probably some chiral centers associated with the brominated vegetable oils inside of Diet Mountain Dew, and that caused a very small amount of rotation. I was surprised at how little it rotated. Regular Mountain Dew, which contains sucrose, typically sucrose or a mixture of fructose and glucose, those are both very chiral compounds, have multiple chiral centers, and we would expect to see a larger rotation because of the greater number of collisions that occur between the high concentration of sugar in regular Mountain Dew and the photons of light. Diet Mountain Dew contains just a trace amount of sweetener, and so you see fewer collisions, and therefore light gets rotated less, even though both sugar and the artificial sweetener are both chiral compounds. So when light gets rotated in this system, it can rotate in either direction, either clockwise or counterclockwise, based on how this system, how the lines here look. It looks like it's rotated counterclockwise and kind of come backwards. So this would end up being referred to as a negative value. This would have a negative rotation. And negative here just numerically means that it's rotating in a negative fashion, not that there's anything wrong with it. Negatives isn't a judgment call on this point. So light rotates left-handed way or negative, or it rotates in kind of the right-handed way or positive. And so experimentally, we can have enantiomers, and one of the enantiomers will rotate light in a negative fashion, and the other enantiomer will rotate light exactly the same numerical value, but in a positive fashion. So these rotations are dextrorotatory, which is right-handed, or levorotatory, which is left-handed or counterclockwise. And we'll come back to this equation in a second. Here is an equation that we use in a lot of these experiments. This is that measured or observed rotation. This is alpha. And if you go back to the experimental design, here it's showing you where you calculate alpha. Alpha is the numerical difference between the polarizing filter and your analyzing filter. And so that's experimentally, this is the value that you record. This alpha is a function of 3 other variables, and you multiply the 3 together to get the measured rotation. And so this variable right here is typically the one that we're interested in finding. So occasionally they will algebraically manipulate this equation so that you solve for alpha brackets, which is the specific rotation. You can think about the measured rotation. This is the sum total of rotation of all of those collisions between the photon and the individual chiral centers. The specific rotation is the amount that each of those collisions causes to rotate. And so what you're factoring out is you're taking that measured rotation and you're dividing out C and L. L is the length of the tube, and C is the concentration of your sample inside of that tube. So if this tube is very, very long, then that means you've increased the probability that a photon will collide with one of your chiral molecules, and so you expect greater rotation. A tube that is twice as long will rotate twice as much. That's L. And L is measured in rather old-fashioned units of decimeters, where 1 decimeter is equal to 10 centimeters, and mercifully, most of the sample tubes are exactly 1 decimeter long. And so if you multiply anything by 1, it keeps the same value. So if your L value, the length of your sample tube, is 1 decimeter, then you can just kind of leave that out of the calculation. You're just multiplying it by 1, or in this case, dividing it by 1. Either way, it doesn't do anything to the math. The concentration is a bit goofy because it needs to be in units of grams per milliliter. And if you've taken general chemistry, you think, well, why not do molarity? Well, The problem with molarity is that you need to know the molar mass of a substance in order to be able to generate a certain molar value. Whereas if you just have grams per mil, you can just weigh out any substance on a scale and get its grams, and you don't actually have to know what the identity of that substance is. And so the concentration in grams per mil allows us to operate and collect data on samples when we don't actually know what the chemical is. We can figure out what its specific rotation is. And I said earlier that this is unique to each individual compound. And so if you know what the measured rotation is, and you know what the concentration of your sample is, and you know what your path length is, you can calculate what the specific rotation is. And from that, you can determine, based on looking up on tables where people have gone through and experimentally determined the specific rotation value, it should match for any molecule. So you can determine experimentally what the compound is. And that's actually a laboratory experiment that we run in the Chem 351L, where we give you an unknown carbohydrate and we give you a table that tells you what the specific rotation of different carbohydrates are. And you measure out a certain mass and you divide it by a certain volume. The path length in our polarimeter in our laboratory is the 1 decimeter, so that just kind of drops out. And then you look at, and then you determine this experimentally in the laboratory, and you can figure out what alpha bracket is. You go back to your table now with your alpha bracket value, and you can identify what the carbohydrate is. Unfortunately, that experiment has a very large margin of error, and I don't know why. We buy all the carbohydrates in high concentrations from a certified vendor. We've checked the polarimeter, we've calibrated it, and it doesn't seem like that's the problem. It just seems like the data always comes out bad. Even when I run the experiment, I fail to get very good data. So I hate that lab just because everybody gets bad data, and I don't know why. So this question down here on the bottom asks, why are the specific and measured rotations different? Well, the specific rotation is essentially a measurement of how much does each collision cause that photon of light to rotate. And the measured rotation is the sum total of all of those collisions. So your specific rotation will be the same for every molecule every time. And the measured rotation will change for the same molecule if you have either a longer path length or a different concentration. So this is kind of a set function of the molecule, and this is a function of the experiment and how you're conducting it. So this is kind of a true value, and this is what we measure in the laboratory and then have to account for mathematically to get that true value. So let's think about what this experiment might look like if you conducted it in the laboratory. So let's consider a solution that we make, and we're going to dissolve 10 grams of 2-butanol in 10 mils of aqueous solution. Now, 2-butanol comes in 2 different enantiomers. Let's kind of look at what those enantiomers will look like. So here's 4 carbons, and this right here would be 2-butanol. Okay? And the enantiomer of 2-butanol, the definition that we're going to use for enantiomers is where you flip all the chiral centers. Well, this one only has 1 chiral center, so if we flip that chiral center, then these are enantiomers of each other. In this enantiomer, the alcohol is going away from me, and there's a hydrogen coming towards me. In this enantiomer, the alcohol is coming towards me, and the hydrogen's going away from me. So these right here represent enantiomers of each other. We can use the R and S stereochemical designations to figure out what these are. And so I'll get my arrow ready. The oxygen right here will be the highest priority functional group. And then of these 2 carbons right here, the carbon that is connected to a carbon and a hydrogen takes priority over a carbon that's connected to 3 hydrogens. So it's going to go from here to here to here. This looks like it's rotating in a counterclockwise or S fashion. But if you remember, the hydrogen is coming towards me. So I'm actually looking at this thing backwards. That means that it's the R configuration because the lowest priority substituent is supposed to be going away from me. And in this particular example, that lowest priority substituent, this hydrogen, is actually coming towards me. And so I'm looking at this backwards. Rather than try to redraw the entire molecule, I just go ahead and determine the stereochemistry while I'm looking at it backwards. And because it looks like it's S, I have to remember to switch my label because I'm looking at this backwards. This other compound over here, I'm just going to grab these arrows and steal them. This oxygen is the highest priority group coming off of this carbon. Then it goes towards this carbon, which is a CH2 group, and then it goes towards the other carbon. So this is rotating also in that S fashion. But since I am looking at it correctly, the hydrogen is going away from me, then this stays S. So this is the S enantiomer, and that's the R enantiomer. These labels R and S are referred to as absolute configurations. I don't have to know any experimental details about the compound to know if it's R or S. The positive and the negative terms are independent of R and S, meaning that just because something is positive doesn't mean it's R and it doesn't mean it's S. We just don't know. So the positive enantiomer of 2-butanol is one of these two, and I don't know which of those two it is. All I know is that this is what R looks like, this is what S is like, and one of these rotates light in a positive direction or clockwise fashion, and so that would be the positive enantiomer. So the question doesn't specify which of the two enantiomers it is. It just says whichever enantiomer rotates it in a positive fashion. And I'm going to put 10 grams of that in a 10 ml aqueous solution. So the math on this one tells me that it asks for the specific rotation. So if you remember the equation, it is that the measured rotation, alpha, is equal to the specific rotation times the concentration times the path length. The question is asking me to find out the observed rotation. So that means that I already have the right equation. So I'm just going to start filling in the variables. These should be symbols right here. If you want, you can fill them in. Whoops. Symbol font is not on my recently used font. So that's alpha right there. And then this is alpha bracket. And hopefully you recognize there are 4 separate variables right here. This one is called the measured or the observed rotation. That's what the question is asking me to find, the observed rotation. This is my specific rotation, that's my concentration, and that's my path length. So that observed rotation is equal to the specific rotation, 13.5 degrees, times the concentration. Now the concentration needs to be in units of grams per milliliter. And I know that I have 0.10 grams per 10.0 milliliters. And then I need to multiply this by my path length, and it tells me that this is a 10 centimeter polarimeter tube. Well, 10 centimeters is 1 decimeter. So this has 3 sig figs, so I'll keep my 3 sig figs there. And don't worry, I don't really care about sig figs, but you should, because you learned that at some point. And it should bother you if you've gotten dumber since you learned that. So this is all multiplication. The number of sig figs should stay the same. It's multiplication and division, so it's just based on the smallest number of sig figs. This has 2, so my answer needs to be reported with 2 sig figs. Now a note on units here. The specific rotation actually has units of degrees per gram per mil per decimeter. So in other words, the units of this specific rotation end up being whatever the units need to be, such that if I put everything else in grams, milliliters, and decimeters, then the final answer will come out in degrees, which is what you want as your value. And this one right here mathematically becomes 0.135 degrees. Whoops. But since there's only 2 sig figs in my final answer, the best answer would be this one right here. This is how much we would expect that to rotate. And that's not that much rotation. In fact, within the margin of error of our polarimeter in the laboratory, I would not be very confident that we would actually see that value come out very well. But yeah, that makes sense. I mean, we're multiplying it by 0.1, and then we're dividing it by 10, so we move the decimal over twice. So yeah. So that would be the observed rotation for this solution in a 10 centimeter polarimeter tube. So then the next question asks us about the enantiomer. So we have a similar solution containing 0.10 grams of the other enantiomer of 2-butanol. And so this right here, this is the same value, this is the same mass, and we're saying everything else is similar. So essentially I'm adding exactly the opposite, sorry, exactly the same amount of the opposite enantiomer. And since the positive enantiomer rotated it by a positive 13.5 degrees, and if we multiply a positive 13.5 degrees right here, that will give us a positive value. If we do all the same math, but instead it's rotating it in a negative amount, then we'll end up with the negative value. And so we can kind of skip the math and say, if you know that one enantiomer rotates it by a certain amount in one direction, then that exact same concentration of the other enantiomer will rotate it exactly the opposite amount. So now we ask the question, well, what would happen if I had a 20 milliliter solution of 0.1 grams of each enantiomer? Or in other words, if I took this 10 ml solution containing 0.1 grams of positive 2-butanol and this 0.1 grams, this 10 ml solution of 0.1 grams of negative 2-butanol, what would happen if I just mix those two solutions together? And the answer is exactly what the math would tell you. We end up with 0 overall rotation. And this leads us to a definition, and this is a racemic mixture. So the term racemic is a useful concept, and this is kind of a vocabulary word for this section right here. A racemic mixture is an equimolar mixture of two enantiomers, meaning that I have exactly the same molar quantities of two enantiomers, and this will have that has a net rotation of a net optical rotation of plane polarized light of 0 degrees. So by definition, whoops, I put these backwards. A racemic mixture will rotate light exactly 0 degrees. That's how we define a racemic mixture. Okay, let's finish up a couple of the other definitions while we're here. Plane polarized light is regular light, if there's such a thing, regular white light. White just means that it has all of the photons of the rainbow. Regular white light that has passed through a polarizing filter. And then optical rotation, this is the rotation of plane polarized light caused by the collision, or it's not really a collision, it's more of an interaction of said light, of plane polarized light. We'll call it PPL. I'm just tired of writing that out all over again. Of the light with a polarizing filter. Nope, sorry, with a chiral compound, chiral center. So the rotation of plane polarized light caused by the interaction of the light with a chiral center. Don't forget that you need to draw a diagram of your polarimeter in here, and that's what I showed you at the beginning of the video in the PowerPoint slide. For the next question, let's consider two separate examples. So here we have a pure sample of A, some compound A, and it rotates light in its pure state in a positive direction, and it has an observed rotation of 10 degrees at some concentration. And so we really don't have a lot of information here. We just know that the measured rotation is 10 degrees. An enantiomerically impure sample of A of the positive and negative has an observed rotation of 5 at the same total concentration. So one of the ways to think about what's going on here is to kind of diagram this. So I like to do this with just a circle right here, and then I use this line. I draw these diagrams all the time. I'm going to use a vertical line right here to show me if I have a racemic mixture, then this compound should rotate light 0 degrees. Okay, so this would be a racemic mixture. Now, there's going to be some maximum rotation. It's not quite centered. That bugs me. I need to zoom out so you can't tell. All right, so there's going to be some maximum rotation. So we're going to kind of stay through the same center point right here. But if we have the enantiomer, if we have the negative enantiomer, because now I'm rotating in a counterclockwise fashion, then we're going to end up with some maximum negative value. So like, let's say a negative 10, whoops, a negative 10.0. So this would be if I had the purely negative enantiomer. At some concentration, it would rotate light a negative 10. At that same concentration, the pure positive enantiomer, let's see if this will allow me to kind of make this diagram sensical. Yeah, the pure positive enantiomer would rotate light positive 10 degrees. And so this kind of represents the maximum spectrum, that I can go somewhere between positive 10 and negative 10. And then the question asks, well, what happens if the rotation comes out as positive 5 right here? So, well, what that tells me is that I don't have pure positive enantiomer. I've mixed in some of the negative enantiomer, but I don't have a racemic mixture, because then it would be 0. And so the first thing you'd ask, well, which one do I have more of? Well, I definitely have more of the positive enantiomer, because if they were exactly equal, then it would be 0. And since they're not equal and it's greater than 0, then that means I have an excess of whichever one is the positive. So which enantiomer is in excess in my impure sample? And the answer is the positive A is in excess, because the optical rotation leans positive. I don't know, right now, I don't know how much excess there is, but I know that I have more of the positive than the negative. Well, now we need to figure out how much more we have. And there's actually a nice little equation for this one, which I drew up at the top, that the enantiomeric excess is equal to the percentage of the major enantiomer minus the percentage of the minor enantiomer. So here, when it's asking me what is the enantiomeric excess of the impure sample, I need to just figure out, well, how much of each of those do I have? And based on how much of each of those I have, then I subtract out the percentages. So if I have 100% of the major enantiomer and 0% of the minor enantiomer, then my enantiomeric excess would be 100%. If I have 99% of one enantiomer and 1% of the other enantiomer, 99 minus 1 tells me that my enantiomeric excess is equal to 98%. And sometimes instead of calling this enantiomeric excess, they will refer to this as optical purity. So in this definition, optical purity or enantiomeric excess is the difference. I think it's the mathematical difference. I feel like mathematical difference is redundant here, but is the mathematical difference between the two percentages of enantiomers. If it's 50-50, then 50 minus 50 gives me an optical purity of 0. If it's 75-25, then 75% minus 25% tells me that my optical purity is 50%. So this question is asking me to calculate right here that enantiomeric excess. It's going to be some percentage value. So this right here is where we need to look at this equation right here. Right? The percentage of the positive enantiomer is equal to your observed value plus your max value divided by 2 times max. So I'm going to steal this equation and bring it down here because I need to know this. The percentage of my positive enantiomer is equal to my observed value. Well, based on the information in the question up there, my observed rotational value right there is 5.0 degrees. And ultimately, I'm going to end up with percent as my unit. So I'm just going to drop off the degree symbol because it's a pain to do the keystrokes for it. And then, so I have the percentage of the positive is equal to the observed value right here, plus the maximum value, which is given to me as 10. And you add those two together, that gives me 15. And then we divide it by 2 times the max. Well, 2 times the max is 2 times 10. And so this ends up being 15.0 divided by, it should be 20.0. That 2 is an exact value if you're keeping track of sig figs. And so 5 plus 10, this is addition rule, so I go out to the tenths place with my answer right there. And then this is 2 times 3 sig figs, gives me 3 sig figs. And you should end up with 0.6 with 3 sig figs, or 75.0%. Oops, wrong. There we go. Okay, so all I did was grab the observed value right there, which was given to me. That's the observed rotation of the positive, plus the maximum value, which was given to me in the first sentence of that, divided by 2 times that max, and then at that you plug everything in your calculator. Now, I didn't use a calculator on this one, and I will give you questions on the exam that don't require a calculator, assuming you can do simple math. And if you can't, then that's on you. You need to be able to do some simple math, and this right here is how I would define simple math. So that's the observed, that is the percentage of the positive. That's not what the question is asking for. The question is asking me for the enantiomeric excess. And the enantiomeric excess is equal to the percentage of whichever enantiomer I have more of. And in part A, I already identified that I must have more of the positive because it leans towards the positive. And then I need to subtract from that the enantiomer that I have less of. Well, if there's only 2 options, and 75% of the option is the positive enantiomer, then that must mean that the other 25% is the negative enantiomer. And so to figure out my enantiomeric excess, that's equal to the 75% minus the difference between 75% and exactly 100%, or 25%, and I come up with a final percentage of 50%. And remember that enantiomeric excess is not asking how much of each enantiomer do I have. That's not what enantiomeric excess says. It's asking how much more of one enantiomer do I have than the other. And it's kind of a weird way of thinking about things, but this right there is the correct answer I'm looking for. Why do people care about enantiomeric excess? Well, the answer is it gives you an indication of your purity. When you conduct a synthesis in a laboratory, when you're building an organic molecule, which I've done, then sometimes you're going to build a chiral center into the compound, and you want to build only one of those enantiomers. And so when I was in graduate school, I worked on a project where my first attempt at the synthesis, I came up with an enantiomeric excess of 98%, which means that I had 99% of the thing I wanted and 1% of the impurity that I did not want. So my enantiomeric excess was 99 minus 1, or 98%, and that wasn't good enough. It needed to be an enantiomeric excess of 99% before I could move on to the next step of the synthesis. So I had to have 99.5% of the enantiomer I wanted and 0.5% of the enantiomer that I didn't want. This is one more example that's not in the lesson plan, but it's useful. So it tells you here that the enantiomerically pure substance has an observed rotation of positive 48.5. And what is the optical purity of an enantiomerically impure sample with a measured rotation of positive 0.12? So we're just going to apply that equation that's down below. The percentage of the positive enantiomer, which is what we're going to solve for first. We want to know the percentage of the positive, is equal to the max. And I've reversed them here. So in the previous one, I called it observed plus max, and I'm using observed and actual interchangeably. But I'm just going to add those 2 values together. The observed value that I actually have, the 1.22, I'm going to add that to the maximum, 48.5, and then I'm going to divide it by 2 times the maximum. So 2 times 48.5. I will go ahead and let you finish up that question on your own. The optical purity ends up being 2.52%. And actually, question B is what we just answered on our way to get to that 2.52%, but I'll let you work through that on your own. Now what I need to do is undo one of the lies. I'll call it a half-truth that I told you before. And what I said before was a compound that has a chiral carbon is a chiral compound. And that's not always the case. There are some exceptions to that. And this right here, this molecule represents an exception to that. And the best way to see the exception and why this compound is not actually chiral is to show it in a Fisher projection. It's just easier to tell what's going on. So what I want to do now is we'll go ahead and use our flying man right here. So I have my Fisher projection all set up, and I need to figure out on the 2 chiral carbons. So this is a chiral carbon. I'll call this one chiral carbon number 2, and we'll call this one chiral carbon number 3. And that maps over here on my Fisher projection that this is carbon number 2, and therefore this right here is carbon number 3. So I'm going to leave those labels over here. And remember, when you're looking at Fisher projections, you want to look at it in such a way that if you were to drop this flying Superman onto the compound, the carbon right there that's chiral would poke their eyeball out. You want to look at the sharp, pointy edge of the carbon. And so that Superman is set up correctly with the head and the eyeball, and then the feet need to be pointed in the direction of the higher numbered carbons. So this carbon up here is carbon number 1, this carbon is carbon number 3, so my eyeball is correct and my feet are correct. And as I look down on this compound from the perspective of this flying stickman, this OH group is coming out of the screen, and therefore it would be on my left-hand side. That means that there's a hydrogen on the right-hand side. And so now to see carbon number 3, it does not work to look at it from this perspective because I'm not jabbing my eyeball on the pointy side, so I need to look at it from underneath. So now I'm jabbing my eye on the pointy side, and my feet down here are in the general direction of carbon number 4, so this is a correct setup. And as I look up at this carbon right here, this OH group, which is going away from the screen, is also on my left-hand side. So both of these carbons right here are chiral, and you can actually give them a stereochemical designation. This carbon is R in my designation. This carbon would be S in my designation. And it goes from oxygen to that carbon to this carbon. So for the chiral centers of this carbon, this is the highest priority, second highest priority, lowest priority of the non-hydrogens. So this is rotating in an R fashion. Over here, this is the highest priority group, followed by the second highest priority, followed by the third highest priority. This also looks very R, but the hydrogen is actually pointed the wrong way, so I need to switch the label, so that's how it ends up being S. So now I have redrawn this compound as a Fisher projection. And what you'll notice is that there is a plane of symmetry right here. And the plane of symmetry means that this carbon right here is the exact mirror image reflection of this carbon up here. And that means that when a photon strikes this carbon and gets rotated by some amount, that photon will strike this carbon and get rotated by exactly the opposite amount. And since there is one of these for every one of these, that means that by the time photons pass through my sample, there's an equal probability that they will hit this carbon as there is this carbon, and so the net rotation will be 0. This is a compound with 2 chiral centers, but does not rotate plane polarized light. And so it's referred to as a not chiral or achiral compounds. And so achiral compounds that have, and usually it has to be 2 or more, so they have 2 plus chiral centers, chiral carbons, are called meso compounds. Meso. And that's, again, a new vocabulary term. There's not been enough today. You have racemic, you have plane polarized light, and you also have this concept of meso compounds. So if we go back to the worksheet, it asks, why is cis 1,2-dimethylcyclobutane achiral? This is a different example than the one that I just showed you. I actually just showed you number 5, so we'll come back to that in a second. But let's go ahead and draw the one that this question asks about. So new document. We'll zoom in a bit. And it's asking me about a cyclobutane. And it is a cis 1,2-dimethylcyclobutane. So cis 1,2, I'm going to put the 2 methyl groups. They simply need to be on the same side. So this right here represents cis 1,2-dimethylcyclobutane. And the chiral centers have been labeled in the name and the auto-generated name by ChemDraw, which is great. But the truth is that when a compound has chiral centers but is not net chiral because it has that internal mirror plane right here, okay? So the left-hand side of this compound is exactly the same as the right-hand side of this compound. They're mirror images of each other. And that means that when plane polarized light gets rotated by this chiral center, it's going to be exactly unrotated or rotated in exactly the opposite amount to give you a net rotation of 0 by the other chiral center. then the correct name of the compound is actually, and this label looks like Meso, sorry, the Meso label should be italicized, just like a cis or trans label. We call this a Meso compound. So cis 1,2-dimethyl cyclobutane is actually correctly called Meso 1,2-dimethyl cyclobutane. Explain why cis 1,2-dimethyl butane is achiral. And so here I'm showing the plane of symmetry, and this compound has an internal plane of symmetry. This means that the chiral centers offset the rotation of plane polarized light, and this means zero net rotation of polarized light, plane polarized light. And the ultimate test of whether or not a molecule is chiral is, does it rotate plane polarized light? And if it's chiral, it does. And if it's achiral, then it does not rotate plane polarized light. And so meso compounds do not rotate plane polarized light, and this is why they're achiral. This last question asks us to draw a Fischer projection for all stereoisomers of 2,3-butane-diol and name each stereoisomer. And so we already came up with one of the stereoisomers of 2,3-butane-diol. And diol nomenclature is not nomenclature you're responsible for, but I figured you'd probably be able to figure it out if I'm helping you with this lesson. So this right here represents one of the stereoisomers. And this particular stereoisomer is referred to as meso 2,3-butane-diol. If instead we had started off with, so here we have RNS. If I just flip, let me get rid of my Superman right here. If instead of RNS, if I were to have put this chiral center right here as going away from me, then that means that over here on my Fischer projection, actually rather than get rid of those compounds, I'm going to copy and paste them. So I'll leave this one alone right here, just kind of leave it there. And then I'm going to take this one and mess with it. So I'm going to flip one of my chiral centers. And if you remember, if you flip one but not all of your chiral centers, then that's the definition of an enantiomer. And what I did is I flipped this chiral center right here. So this now becomes, it's this compound. And this compound right here has an internal, does not have an internal plane of symmetry. In other words, the top half is not a mirror image of the bottom half because the OH groups are on the wrong side. So this is a chiral compound, and the name of this compound would be 2S, 3S, 2,3-butane-diol. And these are supposed to be italicized. When you're submitting your answers, I don't care if you italicize things or not. Okay, and so these two compounds right here are diastereomers of each other. If you have two total chiral centers, then you should be able to come up with 4 different possible stereoisomers. And so now I've got this 2S, 3S, 2,3-butane-diol. Let's go ahead and flip both of my chiral centers. And in doing so, I'll need to flip the chiral centers in my Fischer projections. So notice how this compound right here also does not have that internal plane of symmetry. If I try to put that mirror image up there, the top half and the bottom half are not mirror images of each other because they don't match up exactly. And the bottom one right here is 2R, 3R. Sorry, the name of this compound. And now for the last one, and I saved it for the end because it introduces some new complexity to our life. So I'm trying to organize these as enantiomeric pairs. So if you look from left to right here, I switched both of my chiral centers, meaning that the compound on the left and the compound on the right are enantiomers of each other. Here, the compound on the left and the compound on the right are currently the same compound. So I'm going to try to switch both my chiral centers. So I switch that one and that one. And then over here, I'm going to flip both of these over as well. And so this compound right here does have an internal plane of symmetry right there. And what that means is that it is meso 2,3-butane-diol. And these two molecules are exactly the same thing. They're actually the same. They're not different. You can take a Fisher projection and rotate it head over tail, and it's still valid. So a Fisher projection like this, and if you rotate them head over tail like this, they are the same molecule, just shown from a different perspective. And notice how when I rotate it head over tail like this, it's actually exactly the same as the Fisher projection I had before. And so the point that I'm getting to here is that a meso compound does not have an enantiomer. A meso compound is not a chiral compound, and so its enantiomer, where you try to flip all the chiral centers, just ends up being the exact same compound all over again. So this right here is actually all possible stereoisomers of 2,3-butane-diol. And you might say, but wait, you said that the number of chiral centers is equal to 2, the number of stereoisomers is 2 raised to the power of the number of chiral centers. And I can do this math. I have 2 raised to, there are 2 chiral centers. 2 squared is supposed to be equal to 4. So what's going on here? Well, what I said very carefully, or hopefully I said this if you rewatch the video, is it is equal to the number of possible stereoisomers. There are 4 possible stereoisomers, but it doesn't mean that there are 4 stereoisomers. You can actually have less than that if you happen to have a meso compound that will reduce the number of stereocenters by 1. So it's 2 to the n minus 1 if there's a meso compound. And in this particular case, we just end up with the 3 stereoisomers. The 2s, the 3s, the 2r, the 3r, and the meso compound. These are your 3 different stereoisomers that exist for 2,3-butane-diol. These meso compounds should probably cause you to be a little anxious because it took our fairly simple rules about determining the number of chiral compounds and whether or not a compound was chiral, and it forces you to go through one more step. That before you finish naming a compound, you do have to check for a plane of symmetry. And if the plane of symmetry exists for any one of the reasonable conformations, then that means it's real. And so it does not look quite like this compound right here has an internal plane of symmetry. But if you think about taking this molecule right here and spinning it, I'm going to try it. Just think about spinning this bond right here, okay? And just kind of cranking these around. Okay? Let's go ahead and draw in that hydrogen that's not shown. If I take this methyl group right here and rotate it down to where it's at the position of the OH group. So I'm going to take the methyl group and I'm going to put it down there. I'm just going to rotate this bond right here in the direction that I'm showing. Take the methyl group and rotate it down there. That means that that OH group, which used to be here, is going to rotate up to this position, and that this hydrogen is going to rotate up to that position right there. If we kind of fix this a little bit, and maybe this seems like it's cheating to you, but if we rotate it just a little bit more, what we end up actually doing is we just turned this thing. Okay, so relative to the first molecule that I have, if I just rotate that, this is a possible conformation of the compound, and now without showing a Fisher projection, you can actually see that mirror plane of symmetry. Whereas if I try to do that same type of rotation with this top molecule right here, what you're going to end up with is, I'm just going to rotate this OH group up to where the methyl group is, and I'm going to end up, if I rotate it like that, it actually ends up putting the OH group coming out of the screen. If I try to rotate it 180 degrees, the methyl group will go to this position. And so these two structures right here represent me just rotating this bond 180 degrees. When I do that, the methyl group slides down over here, and this OH group used to be coming out of the plane, but if you rotate it 180 degrees, now it's coming into your field of view. And so there's no mirror plane there. The left half and the right half of this compound don't overlap because the OH group is pointed the wrong way. And so you can try these rotations using the sawhorse diagrams, but the whole purpose of the Fisher projection is really to be able to see those mirror planes much more easily. Let's see, we just have one left. A plane of symmetry. A plane of symmetry is a mirror plane that cuts the molecule into two separate but mirror images. And these are found in achiral molecules, molecules that do not rotate plane polarized light, either because they don't have any chiral centers or that their chiral centers are exactly offsetting, which is the example that we saw in question number 4 and question number 5 on the Meso compound only. So here are the chalkboard problems, the textbook problems, and then there are 3 different chalkboard problems. You guys are going to do essentially the same analysis that I did on number 5. You're going to apply that to 3,4-dimethylhexane, which gives you some practice looking for mirror planes. It also gives you some practice with Fisher projections.